Howdy and welcome back. So, the last section of this lesson is going to be just a brief discussion on some qualitative and quantitative techniques that can be used to kind of analyze our code and beyond the simple means of correctness that test would otherwise communicate. So, beyond correctness, can we give feedback on software beauty? So, well written, readable code. What are the guidelines on what is beautiful? Are there qualitative evaluations that we can employ towards this end? And what quantitative evaluations are available to us? So, qualitative might be to look at, as we're reviewing the code, look at it for code smells. And there's a number of different characteristic code smells or things that suggest that, say, there are deeper problems going on with some sort of block. They're suggestive in the sense that something could be going on here and it could require our attention. To help mitigate code smells, go ahead and write code that is sofa, that is short, does one thing, has few arguments, and is written at a consistent level of abstraction. Now, what do we mean by a single level of abstraction? I kind of alluded to this in one of the previous lessons where I said you can think about this as maybe opening a textbook and you look at the table of contents for the primary chapters. If you read each of those, you can see that it's all kind of at a single level of abstraction. The titles more or less communicate the essence of what's going to be covered within a respective chapter, but we don't get into the actual details in terms of the information that will be disseminated within one. If we were to flip to, say, a chapter, so we're stepping down into a particular chapter, the level of abstraction that would be directly to below, say, the title, would be the sections that comprise that chapter. If we simply gloss over that, we could see the number or the steps that we're going to go through as we're reading through that chapter to acquire the information that the title is communicated to us, that the subject matter will be upon. Now, notice here that the subtitles will all be at kind of a consistent level of abstraction. They'll be kind of one down from the actual chapter title, but they're all kind of descriptive in the same manner. They communicate, okay, well, we're going to cover this, but they don't tell you how they're going to cover it. It's just, okay, expect information will pertain to this particular title. Okay, cool. So if I actually want to look down and learn about, say, that particular thing, I need to enter into that section. So the same can be said about our functions. We want, say, a top level function to have its statements at the same level of abstraction. So it could read like a table of contents. I'm going to do 1, 2, 3. To actually see how those things are implemented, we'd step into that function and we could read, say, its list or its recipe of statements that it will execute to implement the desired behavior. To actually see how those individual behaviors would actually operate, you have to, again, step in. And with each kind of step into a function, you're stepping down one level of abstraction and getting a bit more information. You could think about this. I think the other example I used is like a car. A car could go like forward, backwards, turn left, turn right, what have you. If we had, say, those commands, some combination of them within a function, they're all kind of at the same level of abstraction. It's like, okay, I can go forward. Okay, I can turn left, turn right. I can go in reverse. Now, to actually implement those is going to be a level of abstraction down. For instance, go forward. So you step into that, and that might say something like, ensure the car is in drive, apply pressure to gas, things of this nature. But again, all kind of at the same level. To actually see what happens if you're to apply the gas or shift gears, again, that's going to be, you're going to have to divulge into those functions to see how those lower level of abstractions that allow a behavior to emerge are actually implemented. Now, if you start mixing these, it's going to get very confusing really quickly. So our recommendation, and that of many others, is to always write our code at a single level of abstraction, use functions and the step down principle to kind of reveal more details as necessary. Why are a lot of arguments bad? This is kind of the next thing that we're trying to avoid. Well, more arguments means more combination of testing inputs to ensure that we're properly exercising that named block of code. As we mentioned before, Boolean arguments should always be a yellow flag. We need to really avoid them because if we're passing in a Boolean flag to our function, perhaps we should actually have two different functions to operate to produce that sort of behavior or implement that sort of algorithm. Because again, a Boolean flag would suggest that one of two things is happening. And really, a function should do only one thing, and it should do that one thing well. The other thing, and we've kind of talked about structs to address this, we'll get into this way more when we begin our discussion on classes. If arguments travel in path, maybe you have coordinates x, y, and z of something, and you're consistently passing x, y, and z to a function. Well, this might be kind of good to sit down and think about and go, well, opposed to passing these individually, since they travel in a pact and frequently together, let's go ahead and create a struct called point and go ahead and encapsulate these various variables underneath that hood. So same set of arguments for a lot of methods. It does make sense to really extract out, to refactor and create a type to hold those sorts of things together. Okay. So we're going to get into some quantitative metrics now. What we talked about kind of up to this point was these qualitative code smells, if you will, and a couple of ways to avoid them. We didn't get into what necessarily we were other than saying, hey, they're out there and they can be indicative of problems within our code. To help mitigate this, write short code that does one thing, has few arguments, and is written at a consistent level of abstraction that will increase readability, also help us in crafting our test against that particular block of code. There are also some quantitative metrics that we can apply. These will more or less be calculated using a mathematical formula. One such is going to be the ABC complexity, or assignment branch and condition complexity. This is readily calculated by simply counting up the number of assignment statements, branches, and conditions to come up with a complexity score. The desired value for this would be less than 20, a score of less than 20 for a particular method or function. So why might this be? Well, if we begin looking at this code that has a lot of assignment, branches, and condition, I mean, that's going to grow. And there's probably a point where it could grow to be too large. And then it's starting to do, say, a number of things. And that would be a good point to sit down and refactor, say, code with a huge number of branches, conditions, etc., into maybe well-defined functions with descriptive names. I would also suggest that this could be, a high ABC score could communicate that we have code that may not be doing one thing or is implemented with at various levels of abstraction. So mixing in different levels of abstraction within our code. I will not require you to apply this, use it at all in this class. All I'm saying, the purpose of this slide is to simply communicate that more quantitative metrics exist for our code, and they can be applied to kind of assess the beauty, if you will, of our code. Another one is going to be cyclomatic complexity. This is simply the number of linear independent pathways through a block of code. If you think about it, if we have multiple pathways through our code, what that can mean is, well, we have a lot more pathways that we need to test. So there's some formula on how to calculate this value shown on the slide. What we'd have to first do is convert our block of code and do a graph representation, and then we begin doing things such as counting connected components, nodes, edges, etc. I understand at this point in the curriculum, you probably haven't talked a lot about maybe graph theory and the other things that go into it, specifically how to convert a block of code into this sort of representation. So again, I'm not going to ask you to calculate any of this. I'm not going to ask you to sketch a graph derived from some sort of block of code and tell me, what is the cyclomatic complexity of this block? No, again, this is just pulling your attention to say, hey, here's another quantitative metric that could suggest that, maybe our code's doing too many things at once. If there's a number of linear independent pathways through our code, well, maybe we need to consider how to break that up a bit more, because it's just going to become a burden to actually test. Now, with all of these quantitative metrics, there are target scores. And again, this is not something to memorize. It's just something to be aware of. For instance, code to test ratio, normally a good target score here would be 1 to 2. So more test code than actual code for your implementation. A C0 coverage of approximately 90% would be satisfactory. ABC score of less than 20. Cyclomatic complexity score of less than 10. So again, I'm not going to ask you to calculate these. There are libraries out there which will produce these calculations for you, should you be interested. But again, the purpose of this is to more draw your attention and go, there are quantitative metrics we can use to gauge how our code, different qualities of our code, and then use that to actually assess it and figure out, oh, hey, we have a method with a high ABC score, CC score. Well, maybe we should go in and refactor that into, code where those values are actually reduced.